There is a question that stops working the moment you ask it properly. Not because it's unanswerable, although it may be, but because asking it carefully dismantles the assumptions that made it feel meaningful in the first place. The question is this: what lies beyond the edge of the universe? And the reason it stops working is that the universe, as physics currently understands it, will not have an edge. And if it doesn't have an edge, beyond is not a direction you can point in. And if beyond is not a direction, the question is not a question about a place. It is a question about the limits of human imagination, about what the mind does when it reaches the boundary of what space itself is, and discovers that the boundary is not a wall, but a horizon, and that the horizon moves with you, and that what lies beyond the horizon is not empty space waiting to be explored, but something for which we do not yet have a word. If you enjoy videos that follow a question until the question itself changes shape, that sit with genuine uncertainty without flinching from it or resolving it too quickly, I'd genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's start with the question itself, because the question contains hidden assumptions that need to be pulled out and examined before any answer can make sense. But before we examine the assumptions, let me acknowledge why the question feels so urgent, why it keeps getting asked, why it generates so much discussion, why it refuses to be settled by a simple answer. The reason is that it touches something that is not purely scientific. It touches the limit of what human minds can encompass. Every other limit we have encountered in the history of thought has eventually been crossed. The edge of the known world turned out to be more world. The edge of the solar system turned out to be more solar system. The edge of the Milky Way turned out to be more galaxies. Every horizon in human history has turned out to conceal more. We have learned, over centuries of expanding our view, that the universe is larger than we thought, always larger, consistently, reliably, unexpectedly larger. And so when we now ask what is beyond the edge of the universe, we are asking it against a backdrop of hundreds of years of the universe is bigger than you thought. We have been trained by our own history to expect more. The question is also urgent because it is, at its core, a question about existence itself. Not about what things are made of, that is physics. Not about how things behave, that is also physics. But about whether existence has a limit, whether something has a boundary beyond which nothing begins. Whether the universe is the totality of what is, or whether what is extends past the universe into something we do not yet have a word for. These are questions that philosophy has been asking for millennia, and that science has only recently begun to develop the tools to approach. They are not merely academic. They touch the deepest human concern: what is real, and how much of it is there? The history of human thought about the edge of the cosmos is instructive. Ancient Greek cosmology placed the stars on a crystalline sphere, a physical boundary to the universe, a surface beyond which there was nothing, or perhaps the realm of the divine. The sphere was finite, its beyond was undefined. The question of what lay beyond the crystalline sphere troubled. If the sphere is the boundary of all physical reality, then the question of what is outside it is literally unanswerable within physical terms. arXiv of Tarentum, a mathematician and philosopher of the 4th century BCE, posed what is now called the arXiv paradox. If you stood at the edge of the universe and extended your hand or a stick beyond it, where would your hand or stick go? Either it goes somewhere, in which case there is space beyond the edge, or it is stopped by something, in which case there is a wall, and what is on the other side of the wall? The paradox has never been cleanly resolved. It anticipates with remarkable precision the modern problem. The mind reaches past the boundary and finds that the boundary dissolves under examination. Medieval cosmology added the Empyrean, the outermost heaven, the realm of God, beyond the sphere of the fixed stars. This was not empty space. It was a positive presence, a mode of being that was beyond physical description. The question, what lies beyond the edge, had an answer. The divine. That answer was not scientifically motivated, but it was structurally interesting. It placed something, rather than nothing, at the beyond. The impulse to put something there, to resist the idea of a boundary beyond which existence ceases, is persistent across cultures and eras. It appears in ancient Greece, in medieval Christian cosmology, in Hindu cosmology, in the modern physics of eternal inflation. Something rather than nothing. The something changes. Crystals, God, other universes, other mathematical structures, but the impulse to put something there is consistent. The Copernican revolution displaced Earth from the centre. The Galilean revolution confirmed that the stars are distant suns. The Herschelian revolution mapped the Milky Way. The Hubble revolution revealed that the Milky Way is one of billions of galaxies. Each step expanded the size of the known universe by orders of magnitude and pushed the boundary further away. The current cosmological picture, an observable universe, 93 billion light-years across, within a possibly infinite or very large finite total universe, is the latest step in this sequence of expanding horizons. The pattern suggests that the next step, if and when it comes, will push the horizon further still. The eternally inflating multiverse, if it is confirmed, would be the next step in a sequence that has been going in one direction for 500 years, bigger. This history matters for the philosophy of the question. It means that the answer, the universe just ends, and beyond it is nothing, runs counter to every precedent in the history of cosmology. Every time we have reached a boundary and called it the edge of everything, we have been wrong. This is not a proof that we are wrong again. Induction from past errors is not a logical guarantee of future errors, but it is a reason to be suspicious of any answer that amounts to this time the boundary is real. The scientific and historical track record suggests that the boundary is never real. It is always a horizon, and horizons have beyonds. Now let's examine the assumptions. First, that the universe has an edge, a specific location where it ends. Second, that beyond is a coherent spatial concept, that there is a region of space on the other side of that edge. Third, that whatever is beyond is something rather than nothing, that the question has content. All three of these assumptions are worth questioning, and questioning them takes you somewhere more interesting than any simple answer would. Start with the edge. Does the universe have one? The honest answer is, we don't know, and the question is harder than it sounds. The observable universe, the portion of the universe from which light has had time to reach us in the 13.8 billion years since the Big Bang, definitely has an edge, in the sense that it has a boundary. That boundary is a sphere, roughly 46 billion light-years in radius around Earth, defined not by anything physical at that distance, but by the finite speed of light and the finite age of the universe. Light from further away than 46 billion light-years has not had time to reach us. The boundary of the observable universe is a horizon, not a wall. It is defined by what we can see, not by where space ends. But the universe itself, the totality of space and matter, not just the observable portion, may or may not have an edge. Current measurements of the observable universe suggest that space is geometrically flat, that the large-scale curvature of space is zero, within the precision of our measurements. A flat universe is one in which the angles of a very large triangle add up to exactly 180 degrees, in which parallel lines never converge or diverge, in which the geometry is Euclidean on cosmic scales. And a flat universe, in the standard cosmological models, extends infinitely, not very far, not farther than we can see, infinitely, without bound, in all directions, forever. If the universe is genuinely infinite, then the question what lies beyond the edge of the universe has no referent. There is no edge. There is no beyond. The universe simply continues. In every direction you could point, the universe extends without end, not into empty space. The universe is not embedded in some larger space that it occupies a portion of. The universe is space, all of space. The question of what lies beyond the edge of infinite space is like asking what lies north of the North Pole. It sounds like a question about a place. It is actually a question that reveals the limits of the spatial framework being used to ask it. But here is where it gets genuinely interesting, because the geometric flatness of the universe, the observational fact that space appears to be flat to within our measurement precision, does not actually require the universe to be infinite. A flat geometry is compatible with a finite universe, provided the universe has a topology that allows it to be finite without having a boundary. Consider the surface of a torus, the shape of a donut. The surface of a torus is locally flat. If you are a two-dimensional creature living on the surface of a torus, and you measure the angles of triangles small compared to the torus's size, you will find that they add up to 180 degrees. Your geometry is flat, and some people blaming the triangle. But the surface of a torus is finite. It has a finite area, and it has no boundary. If you travel far enough in one direction on the torus, you return to where you started. The topology wraps around on itself. A three-dimensional analogue of this is possible for the universe. Three-dimensional space could be flat geometrically, and yet finite topologically, wrapping around on itself in one or more directions, so that a traveller going far enough in one direction would eventually return to their starting point, not because they hit a wall and bounced back, but because space itself loops back. A universe with this topology would have no edge and no boundary, yet finite volume. It would be a universe with no outside and no beyond. Not because beyond is empty, but because the concept of beyond does not apply to a space that closes on itself. The question of whether the universe has such a topology, whether it wraps around, is testable, at least in principle. A universe small enough to wrap around within the observable region would produce a specific signature in the cosmic microwave background, matching circles, pairs of circles in the CMB sky that have the same temperature fluctuation pattern, because they are actually the same circle, seen from two different directions after the light has made the loop. These matching circles have been searched for in the CMB data from WMAP and Planck. They have not been found. This does not prove the universe doesn't wrap around. It means that if it does, the wrapping scale is larger than the observable universe. We cannot rule out a topology that wraps at scales we cannot see. So the honest summary of the first assumption that the universe has an edge is this. The observable universe has a boundary defined by our light horizon. The universe itself may be infinite, in which case there is no edge. Or it may be finite, with no boundary, in which case there is still no edge in the ordinary sense. Or it may be finite with a boundary, in which case there is an edge, but we have no observational evidence for this, and the geometry of the observable universe argues against it. The most likely answer, based on current data, is that the universe does not have an edge in the way the question assumes. Now, let's examine the second assumption, that beyond is a coherent spatial concept. Even if the universe did have an edge, a specific place where it ended, the word beyond implies that there is a region of space on the other side of that edge. But the universe, by definition, contains all of space. There is no space outside the universe, because the universe is not a region of a larger space. Space does not exist prior to or independently of the universe. Space is part of the universe. The Big Bang was not an explosion in space. It was an expansion of space. The question of what was outside the Big Bang is like asking what is outside of time. The question assumes a framework, space or time, that does not apply outside the thing being asked about. This is the second place the question breaks down. Even granting that the universe has an edge, beyond requires a spatial framework that extends past the edge, a larger space in which the universe is embedded. There is no evidence for such a larger space. There is no physical theory that predicts it as a necessary feature of reality. The universe is not, as far as any current physics describes it, a bubble floating in a larger, empty space. It is space. All of it. The asking of what is beyond assumes that the universe is an object in space rather than being space itself, and that assumption is not supported by anything we know. Well, but here is where I want to pause, because this is the point at which the question becomes philosophically interesting, rather than merely physically unanswerable. The question, what lies beyond the edge of the universe, persists. People keep asking it, not because they misunderstand the physics, but because there is something in the structure of human cognition that makes it almost impossible not to ask. When we imagine a finite thing, we automatically imagine it is existing within a larger context. A room has walls, and beyond the walls is another room, and beyond that building is the street, and beyond the street is the city. We have no experience of a finite thing that does not have an outside. Every object we have ever encountered has been embedded in a larger spatial context. The very concept of a boundary implies a beyond, something on the other side of the boundary. The universe asks us to abandon this intuition, to accept, not just intellectually, but deeply, that there can be a space that does not have an outside. That a boundary of the universe, if one exists, is not a wall with something on the other side. That the concept of the other side simply does not apply. This is genuinely difficult, not because we lack the intelligence to follow the argument, but because our spatial cognition was shaped by evolution to navigate finite, bounded environments. We did not evolve to intuitively grasp infinite or self-enclosed spaces. The mathematics can describe them. The intuition cannot hold them. And the persistent feeling that there must be something beyond, that the universe must be inside something, is not a logical argument. It is an evolutionary artifact. It is the feeling of a mind built for local navigation, trying to comprehend a question that escapes the local framework entirely. Sitting with that feeling, acknowledging it, examining it, recognizing it as a feature of the mind rather than a fact about the world, is itself a philosophical act. It is the moment when the question stops being about what's out there and starts being about the nature of the asking. Now, let's turn to what physics actually proposes as the relevant context for the universe. Not empty space beyond an edge, but something stranger and more interesting than emptiness. The most developed theoretical framework for what might exist. Beyond, in the sense of at a level of description that encompasses our universe as a component, comes from inflationary cosmology. Cosmic inflation, the theory that the very early universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, was proposed in 1980 by Guth to explain several features of the observable universe that the standard Big Bang model struggled to account for. Inflation works. Its predictions for the statistical properties of the cosmic microwave background have been confirmed to high precision. It is the best supported framework for the early universe we have. To understand why inflation matters for the question of what lies beyond, you need to understand both what inflation predicts about our universe and what it predicts about the context our universe exists in. Let's do both. What inflation predicts about our universe begins with what it was designed to explain. The cosmic microwave background, the oldest light in the universe, released 380,000 years after the Big Bang, when the hot plasma cooled enough for electrons in protons to combine into neutral hydrogen, is extraordinarily uniform across the sky. The temperature fluctuations in the CBM are only 1 part in 100,000. This means the early universe was in an almost perfect state of thermal equilibrium. Hot things in contact with cold things exchange heat until they reach the same temperature. So the early universe's uniformity tells us that all parts of it were in causal contact, in thermal contact, before the CBN was released. But in the standard Big Bang model without inflation, this is impossible. The CMB we see in the northern sky and the CMB we see in the southern sky were emitted by regions that, at the time of emission, were separated by distances so large that light could not have travelled between them since the Big Bang. They were causally disconnected. They had never been in contact, yet they are at the same temperature to 1 part in 100,000. How? Inflation solves this by proposing that before the exponential expansion, the entire region that would become our observable universe was extremely small, small enough to have been in causal contact and to have thermalized. Then inflation expanded it by a factor of at least 10 to the 26th zero in an extraordinary brief time. The uniformity we see in the CMB is the relic of the pre-inflationary thermal equilibrium, stretched to cosmic scales by inflation. Inflation also explains why the universe appears geometrically flat. Any initial curvature of space is stretched away by the exponential expansion, just as inflating a balloon stretches the rubber until the surface appears flat. And inflation explains the origin of the density fluctuations that seeded all cosmic structure, the galaxies, galaxy clusters, and cosmic web we see today. These fluctuations originated as quantum fluctuations in the inflaton field, the quantum field whose energy drove the exponential expansion that was stretched to macroscopic scales by inflation. The specific statistical pattern of these fluctuations, their power spectrum, is predicted by inflation and has been confirmed by the CMB observations of WMAP and Planck to extraordinary precision. The universe we see bears the specific statistical fingerprint of inflation. This observational success is why inflation is taken seriously. It is not merely a clever theoretical proposal. It makes specific, quantitative predictions about the pattern of temperature fluctuations in the CMB that have been confirmed at the percent level by satellite observations. When a theory makes predictions at that level of precision, and they are confirmed, the theory deserves respect. Now, what does inflation predict about the context our universe exists in? This is where eternal inflation enters, and where the implications for what lies beyond become extraordinary. The inflaton field, the quantum field that drove inflation, eventually rolled down to its minimum energy state, ending inflation. In our observable universe, this happened essentially uniformly. Inflation ended at roughly the same time everywhere in what would become our observable universe, releasing the energy of the inflaton field as particles and radiation, the reheating that produced the hot dense state we call the Big Bang. But the inflaton field is a quantum field, and quantum fields have fluctuations. In some regions, quantum fluctuations push the inflaton field upward in energy rather than downward. In those regions, inflation continued, in fact, accelerated, because a higher energy inflaton field drives faster exponential expansion. The probability of these upward quantum jumps is small, but the exponential expansion of the regions where they occur means that the total volume of still inflating space grows faster than inflation ends anywhere. The inflating volume is in this sense self-perpetuating. It never globally ends. New regions have ended inflation. New bubble universes continuously nucleate within the still inflating background, but the background keeps growing. This is eternal inflation. Not eternal in the past, the inflation that produced our universe had a beginning, but eternal in the future. The inflating background will never completely end. It will keep expanding, keep producing bubble universes forever. Our universe is one bubble. Others are forming now, in the sense of now that applies to a context where our concepts of simultaneity do not cleanly extend. They have been forming since before our universe began. They will continue forming after the last star in our universe has burned out, after the last black hole has evaporated, after every structure in our universe has dissolved into a cold, thin, structureless sea of particles at maximum entropy. The eternal inflation picture implies that our universe is not special in kind. It is a typical bubble, or perhaps a selection bias sample of a typical bubble, in the sense that we can only observe a bubble that allows observers to exist. But the process that produced it is not a one-time event. It is an ongoing, self-perpetuating, essentially infinite process of universe production. The multiverse is not a speculation about what might have happened once. It is a prediction of what is happening continuously, right now, in the eternally inflating medium that our bubble universe nucleated within. The region outside these bubbles, the space still in the grip of the inflationary expansion continues to expand exponentially. New bubbles nucleate within it, each becoming a universe. But the exponential expansion ensures that the volume of inflating space grows faster than the bubbles can consume it. The inflation is self-perpetuating. It never completely ends. There is always more inflating space, producing more bubble universes. This is eternal inflation, the theoretical landscape in which our universe is one bubble among a potentially infinite number of bubbles, each separated from the others by a sea of exponentially expanding space that can never be crossed, because the expansion rate exceeds the speed of light in all directions. In this picture, beyond the edge of the universe, if we are speaking of our observable universe, or even of our entire bubble universe, is not empty space. It is other bubble universes, separated from us by the eternally inflating medium. Not nearby, not reachable, not even, in any standard sense, part of the same causal structure, but there, real, in whatever sense the mathematics of eternal inflation is real. Other universes, perhaps with different physical laws, different constants, different histories, an ensemble of existence so vast that the observable universe, with its 2 trillion galaxies and 10 squared constants, is not even a rounding error. This is one of the most disorienting ideas in contemporary physics. It is not proven. It is not even directly testable in most formulations, but it follows naturally from a theory, inflation, that is well supported by observation. And it represents the most developed scientific answer to the question, what is beyond? It is not nothing. It is more of something, more space, more universes, more physics, in a structure so large that our own universe's entire history is a single frame in an incomprehensibly long film. Let me spend time on what eternal inflation actually means, because the phrase other universes is one that gets used casually in popular science and deserves much more careful treatment. A bubble universe in the eternal inflation picture is not a universe in a different dimension or a universe accessed through a portal. It is a region of space-time, continuous with ours in the mathematical sense that both our bubble and other bubbles are solutions to the same equations of general relativity and quantum field theory. That is, causally disconnected from ours. 2 bubble universes cannot exchange signals because the exponentially expanding space between them separates them faster than any signal can travel. They are not in contact. They never were in contact after the moment their respective bubbles nucleated. They are, in the most precise technical sense, separate universes, separate regions of space-time with no causal connection to each other, developing independently from their respective beginnings. What are they like? This is where the physics becomes genuinely strange, and where the question, what lies beyond, acquires real content. In the string theory landscape, the theoretical framework that eternal inflation is often paired with, in which the fundamental constants and even the number of spatial dimensions can take different values in different parts of the landscape. Different bubble universes may have dramatically different physical laws. The mass of the electron might be different. The strength of the electromagnetic force might be different. The cosmological constant, the term responsible for the current accelerating expansion of our universe, might be different, perhaps enormously so. In most configurations of the landscape, the cosmological constant is large enough that the universe would expand so rapidly that matter could never form galaxies, stars, or planets. Only in a small fraction of the landscape configurations, those where the cosmological constant is near zero, as in our universe, then the conditions for complex structure and potentially life arise. This connects to one of the deepest unsolved problems in physics, the cosmological constant problem. The value of the cosmological constant in our universe is extraordinarily small compared to what quantum field theory naively predicts, about 120 orders of magnitude smaller. This is the worst quantitative discrepancy between theoretical prediction and observation in the history of physics. Why is the cosmological constant so small? One possible answer, developed by Steven Weinberg in 1987, before the discovery of the accelerating expansion confirmed that the cosmological constant is non-zero, is the anthropic argument. In the multiverse of bubble universes with different values of the cosmological constant, only the rare universes where the value is small enough allow the formation of galaxies and stars and planets and observers. We find ourselves in such a universe not because our universe was specially designed, but because we could only exist in the kind of universe that allows our existence. The cosmological constant is small in our universe because we are here to observe it, and the kind of observers we are could only exist in universes where it is small. This argument is intellectually uncomfortable for many physicists because it seems to explain a feature of our universe by reference to the fact that we are here to observe it, which feels like circular reasoning. But it is not circular. It is an application of selection effects to cosmology. Just as the fact that you were born implies that your parents survived to reproductive age, a non-trivial fact that needs no further explanation beyond the selection effect, the fact that we observe a small cosmological constant may be explained by the selection effect of the multiverse. Only in universes with small cosmological constants do observers arise to ask why the cosmological constant is small. Whether this argument is satisfying depends on what you think explanation requires. If you believe every physical quantity must be derivable from first principles, the anthropic argument is unsatisfying. It replaces derivation with selection. If you believe that some physical quantities are simply the outcomes of a vast random process, and that the selection effect of being in a life-permitting universe is a valid explanation for why we observe what we observe, then the anthropic argument in the context of the multiverse is a genuine scientific proposal. This is an active debate in theoretical physics, conducted with mathematical rigor and philosophical seriousness, and it has not been resolved. The string theory landscape, which provides the theoretical underpinning for the multiverse of different physical laws, is itself a framework of extraordinary mathematical complexity. String theory proposes that the fundamental constituents of reality are not point particles, but one-dimensional vibrating strings, or, in the more complete M-theory framework, membranes of various dimensions. The different vibrational modes of the strings correspond to different particles with different properties. The specific physical laws in any given region of space are determined by the way the extra-spatial dimensions required by string theory, 6 or 7 dimensions beyond the 3 large spatial dimensions we experience, are compactified, folded up into tiny structures too small to observe directly. Different compactifications produce different physical constants. The number of possible compactifications, the size of the string theory landscape is estimated at something like 10 to the power of 500, a number so large that it exceeds the total number of atoms in the observable universe by many hundreds of orders of magnitude. In the eternal inflation picture, different bubble universes settle into different compactification states, giving them different physical laws. The landscape of possible universes, the set of all possible physical laws that can be realized in some bubble, is the string theory landscape. Our universe is one point in this landscape. The other points are other universes, each with their own history, their own matter, their own potential for complexity, or the absence of it. This is the most scientifically serious answer to the question, what lies beyond our universe, beyond even our bubble universe, is the multiverse, an eternal, self-reproducing structure of bubble universes embedded in eternally inflating space, each bubble a universe with its own laws, each separated from the others by the impassable, expanding medium of inflation. Not empty, not nothing, more universe, incomprehensibly more universe. But I want to hold this lightly, because the multiverse is a theoretical proposal, not a confirmed fact. It follows from a combination of theoretical frameworks: inflation, string theory, the anthropic principle, each of which is itself a proposal rather than a settled matter. Inflation is the best supported of these, with strong observational evidence for its predictions about the CMB. String theory is mathematically sophisticated and internally consistent, but has not made experimentally confirmed predictions distinct from the predictions of other frameworks. We have the multiverse itself is almost by definition untestable. Other bubble universes are causally disconnected from ours, so no observation from within our universe can directly confirm or deny their existence. This is a strange position for a scientific theory to be in, internally consistent, motivated by well-supported framework theories, yet not directly verifiable. Some physicists accept it as a genuine scientific proposal whose truth will eventually be established through indirect argument and internal consistency with other physics. Others reject it as metaphysics dressed in mathematical clothing, unfalsifiable speculation that exceeds the bounds of what science can meaningfully address. The debate is real, serious, and unresolved. There is another class of proposals for what lies beyond that deserves discussion, because it approaches the question from a completely different direction, not from cosmology, but from the mathematics of space itself. So, where was the life of you? General relativity, Einstein's theory of gravity, describes space-time as a four-dimensional manifold, a mathematical structure in which three spatial dimensions and one time dimension are woven together into a unified fabric that can curve, stretch, compress, and twist in response to the presence of mass and energy. The universe, in general relativity, is this manifold. It is not a manifold embedded in a larger space. It is the manifold. The curvature of space-time is an intrinsic property of the manifold, not a feature of how the manifold sits within some external space. But mathematically, manifolds can be embedded in higher dimensional spaces. A two-dimensional surface, a sphere, a torus, a plane, can be embedded in three-dimensional space, and studying the surface in terms of its embedding in the larger space is sometimes useful. The intrinsic geometry of the surface and the extrinsic geometry of its embedding in the higher dimensional space are related but distinct. The intrinsic geometry is what two-dimensional creatures living on the surface can measure. The extrinsic geometry involves the larger space they cannot access. Some theoretical proposals, in particular, certain formulations of M-theory and related brain cosmology scenarios, suggest that our universe might be a four-dimensional brain embedded in a higher dimensional space, sometimes called the bulk. In this picture, the beyond, the edge of the universe is not another region in our three spatial dimensions, but an additional spatial dimension, a direction perpendicular to our familiar space. A fifth or sixth or higher dimension, into which our universe is embedded as a lower dimensional surface. In brain cosmology, gravity can propagate into the bulk, into the extra dimensions, while the other forces, electromagnetism, the strong force, the weak force, are confined to the grain. This is a consequence of the mathematical properties of the forces. Gravity is mediated by gravitons, which are closed strings in string theory and can propagate in all dimensions, while the other forces are mediated by open strings, whose endpoints are attached to the brain. The fact that gravity propagates into the bulk while other forces don't produces an observable consequence. Gravity appears weaker than the other forces at short distances because some of the gravitational field is leaking with a soldiers conflict into the extra dimensions. This is one proposed explanation for the hierarchy problem, the puzzle of why gravity is so much weaker than the other fundamental forces. The extra dimensions dilute gravity's strength. In this picture, beyond the edge of the universe, in the direction of the extra dimensions, is the bulk, the higher dimensional space in which our brain is embedded. The bulk might contain other brains, other universes, parallel to ours, separated by a distance in the extra dimension that is physically real but inaccessible to any force except gravity. When two brains collide, an event called a brain collision, or ekpiosis, the collision releases enormous energy, potentially triggering something like a Big Bang in each brain. In the ekpiotic cosmology of Paul Steinhardt and Neil Turk, our Big Bang was the result of such a brain collision, and the universe undergoes cyclic Big Bangs as our brain in a parallel brain periodically collide, bounce apart, and collide again. This is a radically different picture of what lies beyond, not other bubble universes in an eternal inflation medium, but parallel brains in a higher dimensional bulk. Separated by a gap that might be smaller than an atomic nucleus, in the extra dimension, yet completely inaccessible to anything but gravity. Other universes that are, in a precise geometric sense, right next to ours, separated by a distance smaller than the size of a proton, in a direction we cannot point in, yet as causally disconnected from us as if they were infinitely far away. The question, what lies beyond the edge of the universe, has, in this picture, a geometric answer: another universe, perpendicular to ours, at a distance we cannot directly measure, separated from us by a dimension we cannot observe, but whose effects might be detectable in the anomalous weakness of gravity at short distances. This prediction, that gravity should become stronger at short distances in a specific way, due to the influence of extra dimensions, has been tested experimentally using precision measurements of the gravitational force at millimeter scales. The measurements are consistent with the inverse square law of gravity, down to scales of about 50 micrometers. No deviation consistent with extra dimensions has been found. This constrains the size of any extra dimensions to be smaller than about 50 micrometers, still consistent with the large extra dimension proposals, but constraining their parameters. Before we turn to the question of where the universe is going, I want to address something that seems obvious that turns out, under examination, to be one of the strangest and most important results in all of modern physics. The question of what nothing actually is. When we say what lies beyond the universe is nothing, when we reach for the void as the natural answer, the default answer, the intuitive answer, what exactly are we picturing? The mind generates an image of absolute absence. No space? It may not seem to have been the greatest, but the real question, how we should never be. The mind dispatches the tide. No space, no particles, no power to matter, no real meaning, and no knowledge. The mind, the creepy mind, can dispatch. But here is what modern physics has discovered. That picture is not available in nature. Nothing, as far as quantum field theory can determine, does not exist. Empty space, even the emptiest possible space, the vacuum, the state in which every field is at its lowest energy, is not empty. It seethes, it fluctuates. It churns with activity at scales so small that our largest particle accelerators can only probe the outer edges of the phenomenon. This is the quantum vacuum, and it is one of the most experimentally confirmed and philosophically unsettling results in physics. The vacuum is not the absence of things. It is the ground state of all quantum fields, the lowest possible energy configuration. But quantum mechanics forbids a field from being perfectly static, perfectly zero, perfectly quiet. The Heisenberg uncertainty principle, the relationship between the precision with which you can know a particle's position and the precision with which you can know its momentum, has an analogue for fields. A field cannot simultaneously have a precisely defined value and a precisely defined rate of change. A perfectly empty space, with all fields exactly at zero and exactly static, would violate this principle, so the fields fluctuate. They buzz with quantum activity, even when no particles are present. And from this activity, particle-antiparticle pairs spontaneously emerge, virtual particles, created from the vacuum energy, existing for a brief moment before annihilating each other and returning their energy to the vacuum. These are not hypothetical. They produce measurable, verified effects. The Casimir effect, the attractive force between two uncharged metal plates placed extremely close together in a vacuum, is a direct consequence of the quantum vacuum structure. The virtual particles in the vacuum between the plates are constrained by the boundary conditions imposed by the plates, while the virtual particles outside are not. The difference in vacuum energy density produces a net force that pushes the plates together. This force has been measured. It agrees with theoretical predictions. The vacuum is real, it is active, and it is not empty. The Lamb shift, a tiny but measurable displacement of energy levels in the hydrogen atom, first measured by Willis Lamb in 1947, is another direct or intrusive measures. One thing with conversion is the same thing. The electron in a hydrogen atom interacts continuously with the quantum fluctuations of the electromagnetic field, and these interactions shift its energy levels by a small but specific amount. The theoretical prediction of this shift, derived from quantum electrodynamics, agrees with measurement to 11 decimal places. This is the most precisely tested prediction in the history of science. It depends entirely on the reality of the quantum vacuum, the churning, fluctuating, particle-producing nothing that fills all of space. What does this mean for what lies beyond the edge of the universe? It means that even if we allowed ourselves the framework of beyond the universe is empty space. The framework I argued earlier does not apply, because the universe is space and there is no external space to be empty. Even within that framework, the emptiness would not be empty. The vacuum would be there. The quantum fluctuations would be there. Virtual particles emerging and annihilating would be there. The ground state of quantum fields, with all its structure and activity, would be there. Nothing, the absolute, clean, featureless nothing of intuitive imagination, is not a physical state that nature provides. It is a concept that has no physical realization. This has implications that extend beyond cosmology into some of the deepest questions in philosophy. The cosmologist Lawrence Krauss, in his book A Universe from Nothing, argues that the quantum vacuum is what the universe emerged from. The Big Bang was not a creation of something from absolute nothing in the philosophical sense, but a transition from the quantum vacuum state to a universe full of matter and energy. This argument has been criticized, most notably by philosopher David Elbert, who points out that the quantum vacuum is not nothing, it is a specific physical state with specific quantum fields, governed by specific laws. Calling it nothing is, Albert argues, a rhetorical move that obscures the actual question: why do the quantum fields exist at all? Why are there laws governing the vacuum? Why is the ground state of quantum fields what it is, rather than something else? This is a fair criticism. The quantum vacuum explains how our universe might have emerged from a prior state, but it does not explain why any state exists at all. The question, why is there something rather than nothing, is not answered by pointing to the quantum vacuum, because the quantum vacuum is itself a something, a structured, active, mathematically describable something. The question retreats one level: why is there a quantum vacuum, rather than no quantum vacuum? This retreat is philosophically significant. Every time we try to bottom out at a nothing, to find the floor of existence below which there is only absence, we find more structure, more mathematics, more something. The vacuum is not empty. The vacuum of eternal inflation is not empty. The space between bubble universes is not empty. Every candidate for nothing turns out, under examination, to be a disguised something. This is not a coincidence. It is, I want to suggest, a fundamental feature of how existence works. There is no bottom. There is no level at which you reach the absence of structure and find pure nothing. The question why is there something rather than nothing may be unanswerable, not because the answer is too complex, but because the alternative, nothing, is not physically coherent. We have been thinking about what lies beyond the edge of the universe in spatial terms. But the question has a temporal dimension that deserves equal attention. What came before the Big Bang? What lies not at the edge of the universe in space, but at the edge of the universe in time? The standard answer, informed by general relativity, is that this question is as problematic as asking what lies north of the North Pole. The Big Bang singularity, the point of infinite density and infinite curvature from which all of space-time expanded, is not a moment in time from which the universe emerged. It is the boundary of space-time itself. Time in general relativity is a dimension of the space-time manifold. The Big Bang singularity is the edge of that manifold in time direction. There was no before the Big Bang, because before is a temporal concept, and time does not extend to the other side of the singularity. Asking what came before the Big Bang is like asking what is south of the South Pole. The question assumes a framework that does not apply at that boundary. That here is where it gets interesting, because the singularity at the Big Bang is widely understood to be a signal of the breakdown of general relativity rather than a true feature of physical reality. General relativity is a classical theory. It does not incorporate quantum mechanics. At the extreme densities and temperatures near the Big Bang singularity, quantum effects cannot be ignored. The correct description of the universe at those scales requires a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics, and we do not have a complete, empirically verified theory of quantum gravity. The singularity is where general relativity stops working, not necessarily where time stops existing. In quantum gravity proposals, the Big Bang singularity is often replaced by something more physically reasonable. In loop quantum cosmology, a framework that applies the discrete structure of loop quantum gravity to cosmology, the universe does not begin at a singularity. Instead, the very high density of the pre-Big Bang universe creates a quantum pressure not captured in classical general relativity, a quantum bounce of long-term cosmology that prevents the collapse to infinite density and connects our expanding universe to a preceding, contracting universe. In this picture, the Big Bang is not a beginning, but a turning point. Our universe is one phase of a universe that has been contracting and expanding, bouncing, potentially forever. The question, what came before, has an answer: a contracting universe governed by the same physics getting smaller and denser until the quantum pressure of the bounce reversed the collapse and produced the expanding universe we inhabit. In the Hartle-Hawking no-boundary proposal, a formulation of quantum gravity by James Hartle and Stephen Hawking, the geometry of space-time near the Big Bang is such that the time dimension smoothly transforms into a spatial dimension. In this geometry, there is no sharp boundary, no singularity, no edge of time. The universe has no beginning. In the way a circle has no beginning, you can trace around it endlessly without finding a starting point. The question, what came before, is answered not by nothing, but by there is no before. And this is not a deficiency of the universe, but a feature of its geometry at the quantum level. And then there is the cyclic cosmology, the epcuritic model, in which Big Bangs are produced by the collision of brains in a higher dimensional bulk. In this picture, our universe has undergone an infinite series of Big Bangs, each produced by a brain collision, each followed by expansion and cooling, and the eventual fading of structure, followed by another collision and another Big Bang. The temporal beyond, before the beginning, is, in this picture, more of the same: another cosmic cycle, another brain collision, another era of the universe's existence, stretching back without a first moment. What these proposals share is again the pattern we have seen everywhere. The temporal beyond is not nothing. It is more time, more physics, more structure, or a geometry in which the concept of before dissolves, rather than bottoming out at absence. The universe is not a brief flicker of existence between two infinities of non-existence. It is either part of an infinite cycle, or a bounce from a contracting predecessor, or a geometry that has no beginning in the way a closed curve has no beginning. In every case, more rather than less. The temporal question and the spatial question converge. What lies beyond the edge of the universe, in space or in time, is not the void. It is, in every framework we have developed, more existence of some form. There is one more framework I want to introduce before we arrive at the synthesis, because it approaches the question from yet another angle, not from the geometry of space-time, not from the mathematics of quantum fields, but from a concept that sits at the intersection of physics, mathematics, and computation, information. The physicist John Archibald Wheeler, who spent his career at the intersection of general relativity and quantum mechanics, who coined the terms black hole and wormhole, proposed in his final years a radical idea. He called it from bit. The suggestion was that at the deepest level of physical reality, everything, every particle, every field, every space-time geometry, every physical quantity derives its existence from information, not from matter, not from energy, from answers to yes or no questions, from bits. The universe, in this view, is not fundamentally made of stuff. It is made of information. Physical reality is what information looks like when you are embedded in it. This is a strange idea. It is also, in recent decades, becoming something close to mainstream in theoretical physics. The holographic principle, derived from the study of black holes by Jacob Bekenstein and Stephen Hawking, and formalized by Leonard Susskind and Gerard 't Hooft, states that the information content of any region of space is proportional not to its volume, but to the area of its boundary surface. A three-dimensional region does not contain three-dimensional information. It contains the information that can be encoded on a two-dimensional surface enclosing it. The universe, in this picture, is a hologram, a three-dimensional reality encoded in a two-dimensional boundary. The ADS-C5 correspondence, the most precisely developed formulation of holography, due to Juan Maldacena in 1997, demonstrates explicitly, in a mathematically rigorous setting, that a theory of gravity in a three-dimensional anti-de Sitter space is exactly equivalent to a quantum field theory without gravity on the two-dimensional boundary of that space. The two descriptions, one involving gravity and geometry, one involving flat quantum field theory, describe the same physics. Neither is more fundamental than the other. The geometry of space-time, in the interior, is not more real than the information encoded on the boundary. They are dual descriptions of the same underlying reality. What this suggests, when taken seriously, is that space-time itself may be emergent, not fundamental. Space-time, in this picture, is not the basic substrate from which everything else is built. It is a pattern that emerges from a more fundamental level of description, the information theoretic structure encoded on boundaries. The geometry we experience, the three dimensions of space, the one dimension of time, the smooth fabric of general relativity, is a large-scale, low-energy approximation to something more fundamental, in the same way that the smoothness of water is a large-scale approximation to the discrete structure of H2O molecules. If space-time is emergent rather than fundamental, then the question what lies beyond the edge of the universe changes its character entirely. It is not a question about where space-time ends, It is a question about where the information theoretic structure from which space-time emerges has its limits. And the answer to that question is not given by any geometry of space-time, because space-time, being emergent, does not have the resources to describe its own foundations. This is the deepest version of the problem with the question. The question assumes that space-time is the basic fabric of reality, that the edge of the universe is the edge of space-time, and that beyond the edge is more space-time or its absence. But if space-time is emergent, if it is a pattern in a deeper information theoretic structure, then the edge of space-time is not the edge of reality. It is the edge of a specific physical approximation. Beyond it is not nothing. Beyond it is the deeper structure from which space-time itself arises. The information, the bits, the quantum entanglements, the boundary data from which the interior geometry is reconstructed. We do not know what this deeper structure is, in the case of our own universe. The ADS-CFT correspondence applies to a specific geometry, anti-de Sitter space, that does not match the geometry of our universe, which is a de Sitter space with a positive cosmological constant. There is no established DS-CFT correspondence. The holographic principle in our specific universe is not yet understood at the same level of precision as it is in anti-de Sitter space. But the direction of travel toward an understanding of space-time as emergent from information, toward a picture in which the edge of space-time is not the edge of reality, is one of the most active and most promising in theoretical physics. Today, what lies beyond the edge of the universe? Perhaps it is information. Not empty space, not nothing. The raw informational substrate from which space itself is woven, the bits of which the it is made, the yes or no answers to which every physical quantity reduces, in a framework we are only beginning to construct. The beyond is not spatial. It is not empty. It is the code from which the apparent solidity and extension of our reality is derived. And the code, unlike any physical object, has no spatial extent to end. It does not occupy a location. It does not have an outside. It simply is, and from its being, everything else follows. Before we turn to Tegmark and the mathematical universe, I want to spend time on something that is often missing from discussions of what lies beyond the universe, the question of where the universe is going. Because understanding the future trajectory of our universe is intimately connected to understanding its context. In 1998, two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, discovered that the expansion of the universe is accelerating. Not slowing down, as gravity would cause, but speeding up. Galaxies are receding from each other faster as time passes, not slower. The discovery was so unexpected that the teams initially searched for errors before accepting the conclusion. It earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. The cause of the acceleration, whatever it is, was given the placeholder name dark energy. Dark energy currently constitutes approximately 68% of the total energy content of the universe. Dark matter constitutes about 27%. Ordinary matter, everything made of protons, neutrons, and electrons, everything we can directly observe, everything that has ever been discussed in all of human history, constitutes about 5% of the universe's energy content. We are, in the most literal possible sense, a small minority of what exists, The dominant component of reality is something we cannot directly observe and do not understand. The simplest model for dark energy is the cosmological constant, a term in Einstein's field equations representing a constant energy density of empty space itself. As space expands, more space is created, and the total amount of dark energy increases in proportion to the total volume. This means dark energy never dilutes the way matter and radiation do as the universe expands. Its influence grows relative to matter and radiation over time. The universe will become increasingly dominated by dark energy in the future. The consequences of this for the long-term fate of the universe are stark and, in their own way, philosophically significant. As dark energy drives the accelerating expansion, galaxies that are currently observable will, over the next 100 billion years, recede beyond the cosmic event horizon, the boundary beyond which the recession velocity exceeds the speed of light and no signal can ever reach us. The galaxies of the local group, gravitationally bound to us, will merge into a single large elliptical galaxy over the next few billion years. But all other galaxies, the Virgo cluster, the Coma cluster, the trillions of other galaxies in the observable universe today, will recede beyond the event horizon. Their light will redshift to infinitely long wavelengths. They will become invisible. They will effectively cease to exist for any future observer in our local group as observable entities. 1 trillion years from now, an intelligent civilization living in the remnant of the Milky Way Andromeda merger would look out at a universe containing only their own galaxy and its immediate companions. All evidence of the larger universe, the CMB, the pattern of distant galaxies, the statistical fingerprint of inflation, would have faded beyond detection. A cosmologist in that future civilization, working from first principles, would have no way to infer the existence of the larger universe their ancestors once observed. They would be, in a profound sense, more cosmologically isolated than we are, not because the universe changed, but because the accelerating expansion made their observable portion of it dramatically smaller. This is a sobering thought. We live in a privileged epoch, early enough in cosmic time that we can still see the full extent of the observable universe, still detect the CMB, still measure the expansion history of the universe across billions of years of look-back time. The evidence for the Big Bang, for inflation, for the structure of the universe, all of this is available to us now and will become progressively less available to future observers. We are the last generation, in a sense, who will have full access to the cosmological story. Everything after us works with a smaller and smaller dataset. The fate of the universe itself depends on the nature of dark energy. If dark energy is the cosmological constant, a fixed energy density of space, the acceleration continues at a constant rate, and the universe evolves into what cosmologists call the Big Freeze or heat death. An infinitely expanding, infinitely cooling sea of particles at maximum entropy, where no useful work can be performed and no complex structures can persist. The last black holes will evaporate through Hawking radiation on timescales of 1067 to 1000 years. After that, essentially nothing happens. The universe approaches a state of maximum entropy that is indistinguishable from the vacuum, except that it is expanding. If dark energy is not constant, if it is a dynamical field that evolves over time, possibly growing stronger, the universe faces a different fate: the Big Rip. In the Big Rip scenario, the dark energy density grows without bound, and the force it exerts on smaller and smaller scales increases until it overcomes the gravitational and electromagnetic forces holding structures together. Galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets, then individual atoms, then atomic nuclei, everything at progressively shorter intervals, right down to the subatomic scale, until the universe is ripped apart completely at some finite future time. The DESI survey, currently operating and collecting data on hundreds of millions of galaxies to characterize the expansion history in unprecedented detail, will constrain the evolution of dark energy over the next several years. Its preliminary results, released in 2024, showed hints that dark energy may be evolving, growing weaker over time, rather than remaining constant, or possibly exhibiting more complex behavior. If confirmed, this would rule out the simple cosmological constant model and open the door to a richer picture of dark energy's nature and its implications for the universe's future. The question of what lies beyond the edge of the universe is, in this light, a question that our own universe is progressively answering for itself, not by expanding to reveal what is beyond, but by shrinking its own observable volume, drawing the horizon closer, making the context of our universe less accessible to future observers. The universe is, in a sense, forgetting its own context. We happen to live at the moment when the context is still visible. That is either a coincidence or a selection effect. We exist at the time when stars burn and complex life is possible, which is also the time when the observable universe is large enough to retain evidence of its own origin. That correlation between when complex observers can exist and when the universe is observationally rich is itself a form of the anthropic principle, applied to time rather than space. There is a third framework, entirely different from both eternal inflation and brain cosmology, that addresses the question of what lies beyond from a completely different direction: the philosophy of mathematics, and specifically the mathematical universe hypothesis proposed by cosmologist Max Tegmark. Tegmark's argument begins with an observation. The universe appears to be described by mathematics, not approximately, not as a useful model. The universe seems to be mathematical in the sense that its laws are expressed in mathematical structures, and that mathematical reasoning about those structures produces accurate predictions about physical reality. This is, on reflection, strange. Why should the universe be mathematical? Why should abstract structures invented by human minds to solve problems in counting and geometry turn out to describe the behavior of subatomic particles and the expansion of space-time? Physicists have noted this unreasonable effectiveness of mathematics since at least 1960, when Nobel laureate Eugene Widner formalized the observation in an influential essay. It is genuinely puzzling. It is now a world one. Mathematics is, on the face of it, a human activity. We define axioms, derive theorems, develop structures. Nothing in the process of mathematical reasoning guarantees that the results will describe physical reality. A mathematician can define an entirely consistent mathematical structure, say a non-Euclidean geometry, or a finite field, or a higher dimensional manifold, without any reference to the physical world. And yet, these structures repeatedly turn out to describe physical reality with astonishing precision. Non-Euclidean geometry, developed as a pure mathematical exercise in the 19th century, turned out to be the geometry of space-time in general relativity. Complex numbers, defined as extensions of the real numbers, for purely algebraic reasons, turn out to be essential to the formulation of quantum mechanics. Group theory, developed in the 19th century to study abstract symmetries, turns out to be the language of particle physics. Tegmark's proposal is that the universe is mathematical, not because mathematics is a useful description of it, but because the universe is literally a mathematical structure, not described by mathematics, made of mathematics. The physical universe, the specific four-dimensional space-time manifold with its quantum fields and particles and constants, is a mathematical object, in the same sense that a circle or a prime number is a mathematical object. The difference between the circle and the universe is not that the circle is abstract and the universe is concrete. It is that the circle is a simpler mathematical structure and the universe is a more complex one. Tegmark distinguishes 4 levels of multiverse, of which the mathematical universe is the 4th and most extreme. Level 1 is the region beyond our observable universe, in the eternal inflation picture. More of the same universe, with the same physical laws extending to scales we cannot observe. Level 2 is the bubble universes in eternal inflation, regions with different physical constants due to different compactifications of extra dimensions or different configurations of the inflaton field. Level 3 is the Everett many-worlds interpretation of quantum mechanics, in which every quantum measurement produces a branching of the wave function into parallel versions of reality, each equally real. Level 4 is the mathematical universe, the ensemble of all consistent mathematical structures, each of which is equally real. The Level 4 multiverse is the most radical and the least constrained. Every mathematical structure that can be defined, every set of axioms, every geometry, every algebraic system corresponds to a universe in the Level 4 multiverse. Most of these structures do not resemble our universe at all. Most do not have anything that looks like particles, or space-time, or laws that allow complex structure, but some do. And in those, if the structures allow for self-aware substructures, systems that model their environment and themselves, those substructures experience their structure as reality in the same way we experience ours. This is a stunning proposal. It amounts to saying that the question, why is there something rather than nothing, has a trivially true answer. Mathematical structures exist as mathematical objects, and existence as a mathematical object is the same as physical existence. Everything that is mathematically possible is physically real. Our universe is not a special case. It is one of infinitely many, equally real mathematical structures. And the only reason we find ourselves in this particular structure is that this particular structure allows self-aware substructures to exist, and we are one of them. The implications for what lies beyond the edge of the universe are profound. In the Level 4 multiverse, the beyond is not spatial at all. It is the space of all mathematical possibility, an infinite library of structures, most of which contain no observers, some of which do, and our universe is one of the ones that does. The beyond is not empty space, not other bubble universes, not other brains. It is other mathematical realities, other sets of rules, other forms of existence, other ways of being organized, and there is an infinite number of them, and they're all equally real. Whether this is science or philosophy is a genuine question that Tegmark himself engages directly. He argues that it is science, in the sense that it is the most parsimonious explanation for the unreasonable effectiveness of mathematics, and that it makes the testable prediction that our universe should have the properties of a high, computationally simple mathematical structure, because simple structures are more common in the mathematical universe, and if we are a random sample of observer-containing structures, we should expect to be in a relatively simple one. Whether our universe is simple in this sense is debatable. It is described by a fairly small number of equations and constants, which might qualify as simple relative to the space of all possible structures. Others argue that the mathematical universe hypothesis is unfalsifiable metaphysics, that the claim every mathematical structure is real cannot be tested by any observation made within any particular mathematical structure, and that a claim that cannot be tested is not science. This is a serious objection, and Tegmark's responses to it are interesting but not universally considered adequate. What the mathematical universe hypothesis contributes to the question at hand is this: it provides the most extreme possible answer to what lies beyond. Not more space-time, not more universes, but more existence of every conceivable kind. It takes the question to its logical limit, past the limit of space-time, past the limit of physics, into the space of all possible consistent structures, and offers an answer that is simultaneously the grandest possible answer and the emptiest of empirical content. Everything that can exist, exists. Our universe is everything that our particular set of rules produces. Beyond it is everything that other rules produce. The beyond is the infinite library of all possible mathematics, and our universe is one book in it. Now, I want to bring in something that the formal theoretical frameworks sometimes obscure: the role of consciousness and observation in these questions. Because the question, what lies beyond the edge of the universe, is not purely a question about objective reality. It is a question asked by a specific kind of entity, an observer, a self-aware system, from a specific vantage point, inside the universe, embedded in it, made of it. And the relationship between observers and the universe they are embedded in is one of the deepest and least resolved problems in physics and philosophy. In quantum mechanics, the role of observation is fundamental and controversial. The quantum state of a system, described by the wave function, evolves deterministically according to the Schrödinger equation until an observation is made. At the moment of observation, the wave function collapses to a specific definite value. The mechanism of this collapse, what constitutes an observation, whether consciousness is required, whether collapse is real or apparent, is the measurement problem of quantum mechanics, and it has been debated for nearly a century without resolution. Different interpretations of quantum mechanics, the Copenhagen interpretation, the many worlds interpretation, the pilot wave theory, the relational interpretation, and others, give radically different answers to what is happening during measurement and whether the collapse is real. This matters for the question of what lies beyond, because some interpretations of quantum mechanics, particularly the many worlds interpretation, have implications for the nature of reality that connect directly to the multiverse discussion. In many worlds, every quantum measurement produces a branching of the universe into multiple versions, each with a different outcome of the measurement. These branches are all equally real. They do not interact with each other after branching. They are effectively separate universes, embedded in the same fundamental mathematical structure, but causally disconnected after the branching event. In many worlds, The multiverse is not something that exists in distant regions of space, separated from us by the inflating medium. It is something that is being continuously produced here and now at every quantum measurement event. The beyond, in many worlds, is not spatial. It is the collection of all branches, all versions of reality produced by all quantum measurements since the beginning of the universe. And we are in one branch, unaware of the others, because the branches do not interact. If many worlds is correct, the question, what lies beyond the edge of the universe, has a different answer than the one eternal inflation provides. Beyond is not other bubble universes in distant regions of an inflating space. Beyond is other branches of the same quantum wave function, other versions of this universe, differing in the outcomes of quantum measurements at every scale, from the subatomic to the cosmological, all equally real, all coexisting in a Hilbert space that contains our branch as one among an unfathomably large number. The answer to what lies beyond is not one thing, it is many things, depending on which level of structure you are asking about. At the level of our observable universe, more universe, possibly infinite, with the same physical walls. At the level of eternal inflation, other bubble universes with different physical constants. At the level of many worlds, other quantum branches of this universe. At the level of string theory landscape, other compactifications, other physical laws. At the level of the mathematical universe, every possible mathematical structure. Each framework provides a different answer, and each answer involves more rather than less. More existence, more structure, more reality. What they share is the negation of the simplest intuition that beyond the edge of the universe there is nothing. That intuition is wrong at every level of analysis. Every framework for thinking seriously about the foundations of reality places something, more existence of some kind, beyond our observable horizon. The universe is not a bubble of being in a sea of non-being. It is one part of a vastly larger structure, the nature of which we are only beginning to understand. This convergence, the agreement across radically different frameworks that the answer involves more rather than nothing, is not a coincidence. It reflects something deep about the nature of existence, that existence, once it exists, tends to be more extensive than any finite description can capture. That the totality of what is real is always larger than the totality of what any observer embedded within it can directly observe. That horizons are not walls, but limits of sight, and what is beyond the limit of sight is not absence, but mru. There is a final layer to this question that deserves explicit attention: the limits of our own concepts. The frameworks I have described, eternal inflation, brain cosmology, many worlds, the mathematical universe, all use concepts developed within our universe to describe something that, by definition, is outside the framework in which those concepts were developed. Eternal inflation uses the concepts of space-time, quantum fields, and probability, all concepts derived from the physics of our universe, to describe a context that encompasses our universe. Brain cosmology uses geometry, the mathematics of higher dimensional spaces, developed by humans embedded in a four-dimensional spacetime. Many worlds uses quantum mechanics, a theory developed to describe the behavior of systems within our universe, to describe a structure that contains our universe as one branch. The mathematical universe hypothesis uses mathematics, a human activity conducted in a specific cultural and cognitive context, to describe the totality of existence. All of these frameworks are, in a fundamental sense, extrapolations. They take tools that work within our universe and extend them beyond the domain in which they were verified. This is not automatically a mistake. The history of physics is full of successful extrapolations of this kind. The laws of physics discovered on Earth were extrapolated to describe the behavior of stars and galaxies and the early universe, and the extrapolations worked. But there is no guarantee that the next extrapolation, from our universe to whatever is beyond, will work in the same way. The concepts of space-time, quantum fields, probability, and mathematics are all concepts we developed within a specific physical context. It is possible, genuinely possible, that those concepts do not extend cleanly to the description of whatever is beyond that context. That the beyond, if it exists in any sense, is described by a framework that we do not yet have and that may not be constructible from within our universe. This is the deepest form of the question's difficulty. It is not that we haven't looked hard enough or built powerful enough telescopes. It is that we may be using the wrong tools built for a different job, to try to answer a question that requires new tools we don't yet know how to construct. The beyond may be real, it may be vast, it may be more interesting than anything our current frameworks can describe, but it may also be, for now and for a long time, beyond the reach of any description we can formulate. That is not a failure. It is the appropriate humility of a species that has been asking questions for a few 100,000 years about a universe that is 13.8 billion years old. We are early. Our tools are young. The question is old, older than any human civilization, as old as the first mind that looked up at the boundary of the known and wondered what was past it. The wondering is not wasted. Even if the answer is currently beyond our reach, the act of reaching, of developing frameworks, testing them against observation, extending them carefully and honestly past their verified domain, is how the tools get built. The cosmologists working on eternal inflation today are building the conceptual tools that will allow their successors to say something more precise. The physicists working on string theory are exploring the mathematical landscape within which the next theory of everything might be found. The philosophers examining the foundations of the mathematical universe hypothesis are clarifying the questions that physics will eventually have to answer about the relationship between mathematical structure and physical existence. The theorists pursuing emergent spacetime from information are dismantling one of the most fundamental assumptions in the history of physics, that space is the given, not the derived, and building something stranger and more general in its place. Each of these endeavours is incomplete. Each faces objections that have not been resolved. Each is working at the edge of what current mathematics and observation can support. But the frontier is where the interesting questions live. The comfortable centre of any field of knowledge is where the answers are. The edge is where the questions are still alive, still kicking, still capable of surprising you. And this question, what lies beyond the edge of the universe, is alive. It has been alive since the first human being looked up at the night sky and wondered where the stars ended. It is still alive now, in the pages of theoretical physics journals, and in the calculations of cosmologists trying to extend the reach of observation beyond what light can show us. The universe is 13.8 billion years old. It contains, in the observable portion alone, something like 10 squared stars. Its total extent, if it is infinite, is larger than any number we can meaningfully write. If it is finite, it is still larger than any number we have intuitive access to. And beyond it, in whatever sense beyond applies, there is, according to the best current theories, more, not less, not nothing, more existence, more physics, more mathematics, more universe, more information, more time, more structure, of every kind that the laws of logic and mathematics permit, all of it equally real, all of it part of what is, rather than what isn't. The universe is not a bubble of existence in a sea of nothing. It is one part of a vastly larger structure, spatial, temporal, informational, mathematical, that we are only beginning to map. The nothing is not an option that any current physical or mathematical framework makes available. There is always more, always has been. Every horizon has revealed another horizon. Every framework, pushed to its limits, has disclosed a larger context. Every question about the boundary has discovered that the boundary is not a wall, but a doorway. And what is through the doorway is not absence, but more of a different kind. That is not a comfortable answer. It does not resolve the question. It transforms it. And transformation is what happens when a question is asked well. What lies beyond the edge of the universe? More. That is the answer every framework converges on. More existence, more structure, more reality, more than we can currently see, more than we can currently describe, possibly more than we can currently imagine. But we are imagining, and the imagining is not stopping. The question keeps working, even after it breaks the assumptions it started with. It works because it is not really about what is out there. It's the most important part that will ever be. It is about what we are, minds that reach past their own boundaries, past the edge of what they can see, past the limits of what their concepts can grasp, and find, every time, that there is more. That the reaching is rewarded not with an answer, but with a larger question, that the horizon moves with you, that the universe does not end, that what lies beyond is not the absence of something, but the presence of something we don't yet have the language to name. You are standing on a rock, hurtling through space, surrounded by 2 trillion galaxies, at the edge of what light has had time to show you, looking out at a horizon that recedes as you approach it, into a beyond that is not empty, a beyond that seethes with quantum fluctuations, even in its most barren corners. A beyond that contains other universes, bubble universes, grain universes, branching quantum universes, mathematical universes, each as real as the one you are standing in, each unreachable, each part of the same answer, more.